So you missed lesson 4.2.5. It's got a cute name, Fuelish Choices, because it's all about evaluating different fuels. So first in Chem Catalyst, it's got some great balancing practice, and all these fuels are actually used in cars. So some of the cars in the Indianapolis 500 use methanol instead of what we use typically, which is octane. And then also some race cars use nitromethane as a fuel. So first we need to balance these. We know if there's only carbons, hydrogens, and oxygens to balance in that order. So let's talk through this. There's 8 carbons on the left, so I'm going to need 8 carbons on the right. There's 18 hydrogens on the left, so I'm going to need to have 18 on the right. 9 times 2 is 18. Now for oxygens, I've got 16 plus another 9 oxygens, that's 25. That's an odd number. So temporarily I can put a 12.5 because 12.5 times 2 is 25 on that left oxygen. And I can't leave it that way, so I'm going to double all of my coefficients for my final answer. For number 2, same thing. Let's go carbons, hydrogens, oxygens. I'm going to start with the carbons, which are already the same on both sides. 1 on the left, 1 on the right. Hydrogens, I've got 4 on the left and only 2 on the right. So I'm going to throw a 2 there. And my oxygens are not right. There's 2 plus another 2, that makes 4. Here there's 2 plus only 1. So couple of things I could do here. I could use a decimal because 1.5 times 2 is 3, and now everything is balanced. But I can't leave that decimal there, so I'm going to multiply everything by 2. 2, 3, 2, 4 for my final coefficients. And then in the last one, I've got 1 carbon on each side. That's good. 1 nitrogen on each side. 3 hydrogens, only 2 hydrogens. So that doesn't work out. So I'm going to try by starting with a 1.5 in front and see where that gets me. Now I've got 2 oxygens plus 1.5 plus another 2. That's 5.5. I've got 2, 4, 6. So that doesn't really help me. So sometimes this happens in balancing. You got to go back to the drawing board and say, okay, what can I do here? So since my hydrogens are an odd number, I'm going to start by making this odd number even. So I'm going to throw a 2 in front, which changes my carbons and my nitrogens. So now I've got 2 times 3, 6 hydrogens. So if I throw a 3 in front, 3 times 2 is 6. Let's count all my oxygens. I've got 4 plus 3 is 7 plus 4 is 11 oxygens. On the left side, I've got 4 here, and I need 7 more. So I can temporarily use a decimal. 3.5 times 2 is 7. So now I can double everything and get my correct coefficients. 4, 7, 4, 6, 4. And there's lots of different things to consider when you're driving. And I mean, a lot of it has to do with, are you racing? Do you need to be able to use more fuel in a shorter amount of time? And things like that. Do you need the fuel source to have oxygen within it? Because that is what, giving you a little hint about nitromethane, check it out. It has its own source of oxygen. Let's take a look at the activity together. There are a whole bunch of different fuels listed with how much energy they release per mole. And obviously we're seeing that octane is releasing that highest amount in calories per mole. And the lowest is hydrogen. And you'll also probably notice that octane was the largest and hydrogen was the smallest. Number 2 says, look at methane, which has 1 carbon, and compare it to ethane. What happens to the energy output as carbon atoms are added? Does that pattern hold up? So methane, about 200,000. Ethane, almost 400,000. Butane, almost 700,000. Hexane, it keeps going up and up and up. So as the number of carbon atoms increases, so does the energy output. And yes, the pattern works for all the fuels in that table. Now we're going to look at what happens when you add an oxygen to the molecule. So let's compare methane versus methanol. They're very similar, only methanol has an oxygen. It's a little bit lower of an output. Same with ethanol, a little bit lower than ethane. Same with butanol, a little bit lower, and hexanol. So there's a less energy output with oxygen in formula. And yes, this pattern does hold true for all of the fuels in the table. And then what if we needed to predict the energy output for propane? Because it went 1 carbon, 2 carbons, 4 carbons. So I would guess somewhere in the middle of 687 and 373. Maybe around 500,000 units were calories per mole. For number 5, it says it wants us to convert these into energy per gram. So using the chart, it says kilocalories per mole. I'm noticing that these numbers are the same as the ones up here, only they're divided by 1,000. So I'm going to fill in the missing ones. Hexanol's 951, 687, 327, 174, and 175. Molar mass is something we did a while ago that's looking at the periodic table and adding up the molar masses of these atoms. So 8 carbons, which each weigh 12 grams per mole, plus 18 hydrogens, which each weigh 1 gram per mole, adds to 114. So it'd be a great practice for you to pause the video and add up these other missing molar masses here. This one ends up being 44. Oh, that can't be right. That seems too small. Let's figure out this one again. So we've got, type this in over here, 6 times 12, 72. And then we've got 14 plus 72 plus the 16 oxygen. So this ends up being 102 for hexanol. And so if we do the kilocalories per gram, we're going to do 951 divided by 102. And that comes out to be 9.3. Butane comes out to be 11.8. Butanol, 8.6. Ethane had a molar mass of around 30, so 12.4. Ethanol, 7.1. Methane, 13.3. Hydrogen, 29. And nitromethane, 2.9. Then it says list the top 6 fuels in terms of the amount of energy released per gram. Well, hydrogen's number 1, and methane's number 2, ethane's number 3, and then we've got 11.8 for number 4, we've got 11.5 for number 5, and octane for number 6. Couple making sense questions here. It says, hydrogen is also used as rocket fuel and in fuel cell vehicles. How many grams of octane would be needed to produce the same amount of energy as 100,000 grams of hydrogen? Well, 100,000 grams of hydrogen, according to the table, it produces 29 kilocalories for every 1 gram. So 100,000 grams would produce 2,900,000 kilocalories. Octane produces 11.4 kilocalories per gram. So we can divide to learn that you would need 254,386 grams of octane to release the same amount of energy as just 100,000 grams of hydrogen. So you would need 2.5 times as much. Do you think the best fuel is the one that has the greatest output in calories per mole? Not necessarily. The one that produces the most calories per mole is also larger, heavier molecule. And so you would want to take that into consideration if you're racing, for example, and you only have so much space for fuel. Which fuel would you expect to release more energy, methane or propane? Well, as we discussed earlier, the energy per mole, whichever one is larger, produces more energy. And then in class, we lit some bubbles on fire, and so look to the other videos for that demonstration. That should give you enough background to be able to get started on the homework. It's just extra practice and more thinking about fuels.